Well, good morning, everybody. I see we still got a few people straggling in here. Give you a little bit of a heads up what we're going to do today. We are going to start off, we got to change things up and have a little bit of fun. So we'll start off with a Kahoot. And the Kahoot's going to be about steam traps. We're not there yet, but we will be there in a little bit. And so just a bit of a Kahoot refresher on steam traps. Maybe we'll squeeze in a couple of new things that maybe weren't on your list last year for steam traps. Then what we're going to do is we're going to get back into piping, and you know this PowerPoint stuff just exhausts me. So we're going to see a few videos today. They're short little videos. I think there's 5 of them, and each one's 1 minute long, but they're so good. And then after we do that, we'll have a break sometime in there. I'm not too sure exactly when. And then we'll come back and we'll start doing steam traps and looking at hammer and steam trap sizing. I think that's really the main new thing for third class. How do you select the steam trap that's the right size and the right application? So we'll get into that a little bit later today. And I see that there are now 15 people in the room. So how about right now y'all get your Kahoots ready and we'll get your Kahoot on. All right. Lobby music. Randomize order of answers. Show minimize intro. Da, 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 da. All right, I think we're ready to go here. I can't remember how to start the game. So classic, game options, general, advanced. What's the matter with me? I've forgotten how to start the game. Hide the game options. Classic. Okay, here we go. Am I waiting for anybody else? Oh. 10. There's 17 in the class right now. Should I wait? Okay, we're gonna lock the room. Oh, 11. Okay, we'll lock the room now. And away we go. Okay, so looks like everybody selected thermostatic, but yeah, they work on mechanical and thermodynamic principles. So those are the three categories of steam traps: thermostatic, thermodynamic, and mechanical. Okay, it's an F&T. It's got this unmistakable float, and there's the thermostatic element. Anybody know what the thermostatic element is for?
To let out air.
Exactly, yeah, it's an air vent. Yes, you got it, inverted bucket. So there is the actual bucket. Right on. Yes, so this one works not on thermostatic principles, but thermodynamic principles. So it's a thermodynamic trap, and it's also called a controlled disk thermodynamic trap. Good job. Yeah, this is a thermostatic. It's got some kind of a bellows inside um, that when it gets hot, it closes, hot due to the presence of steam. And then as condensate collects, the condensate is cooler, so it opens up and discharges condensate. Wow. Yes, it's a liquid expansion. So for you guys here, uh, was this covered in the fourth class? Did you guys look at liquid expansion steam traps?
No,
Not that I
no.
remember, no.
Okay, so here's the interesting thing. It's a thermostatic trap. See, this is one of the new things I'm kind of slipping in. It's in your third class. So there's a thermostatic element in there, and it kind of works like a thermostatic trap. But at this end here, where there's that kind of like a nut, you can actually adjust the condensate discharge temperature. So you can discharge relatively low temperature condensate at 60 degrees. You can um, discharge condensate that's 100 degrees. And it has certain applications and advantages, but also has certain disadvantages. It's really kind of old school, and I sort of wish that it wasn't in the textbook because it's been superseded by a type of trap called a balanced pressure trap. But one of the problems that they have is that they back up condensate. So if you're discharging condensate at 60 degrees Celsius, that means that the condensate's got to cool off for a really long time. And if you've got a really high pressure steam, your condensate saturation temperature might be, say, 150 degrees Celsius, and you got to wait for that condensate to cool off to 60 or maybe even 100. So it has certain applications and certain interesting uses, but that's a liquid expansion. Oh, good job. Okay, so let's just take a look at these here. You know what water hammer is, and water hammer can damage steam. And one of the things that we can think of when we're selecting traps is, do we want something that's, say, resistant to freezing? Do we want one that's resistant to water hammer? This type of stuff. And so basically anything that's got a float inside, that float can be actually crushed by a water hammer. So floating thermostatic, a great trap, but one of the things about an F&T is they are susceptible to water hammer. Now, on a lot of people pick 5 thermostatic, and I must say that yes, thermostatic traps, they can either be damaged by water hammer or not be damaged by water hammer. So for example, let's say we've got a thermostatic one that's got a little bellows in there, and the bellows has a volatile liquid, and it expands and contracts the bellows and operates the trap. That definitely is susceptible to water hammer, because the hammer will damage, collapse the bellows. But another type of thermostatic is the bimetal, and that shouldn't say bimeta, I should say bimetal. That's a typo. Bimetal is a thermostatic trap, but it has a bunch of elements that are responsive to temperature of the steam, and that particular one is not susceptible because you have this little pressure vessel or this little float. And the inverted bucket, of course, is a mechanical trap like the F&T, but instead of having an enclosed ball, it has an open ball. It's got a bucket, right? And so that the pressure equalizes on both sides of the bucket will not collapse if there's a water hammer. So you could argue that the thermostatic one is kind of half true. Here, for example, is an inverted bucket trap. A picture that I took somewhere, I can't remember where. Yeah, I gave that one away, but I do like this animated GIF. That's pretty cool. So that, I showed you the picture of the outside of one of these types of traps made by Spirax Sarco. This is an animation by Spirax as well. It's kind of neat how it shows the thermostatic element responding to the temperature. Now, the thing is that this one here has a bellows inside, and that bellows is filled with liquid, um, non-volatile liquid. Uh, so think of that as we get into traps a little bit later. There's a non-volatile liquid that expands and contracts and operates the bellows. Whereas you see that some of them are going to have a volatile liquid. The volatile liquid is very interesting because it will cause uh, the trap to respond to a pressure curve as system pressure changes. And we know that when the system is cold, the pressure is relatively low, and then eventually it warms up, and then the steam pipes warm up, and then the steam pressure rises until the steam pipe is all warmed up, and we reach some kind of a temperature corresponding to the temperature and pressure of the steam. And so you'll see that ones with volatile liquid will actually follow that pressure curve as the steam pipe heats up. Dewinder, you're the man. Good job. Yeah, got that one right. So one of the things that we care about is venting air on startup primarily. I mean, when we start up a system, we've got air inside the pipes, and we have to get that air out. We don't want heat exchangers to be air locked and air bound. And so if we can discharge the air with the condensate into the condensate return tank, then the air gets vented out, and then the condensate returns to the boiler. But we want to get the air out of the steam, basically due to Dalton's law of partial pressure. So if we have got air in the system, it's occupying a certain amount of space. It's part of the pressure, and the temperature will be less because the air is occupying a certain part of that space. So we got to get rid of the air from the steam system. When and where do we get rid of it? Primarily on startup, but times we do volatilize some carbon dioxide and some other things that we can kind of categorize as air. We'll volatilize perhaps a little bit of carbon dioxide in the boiler, especially if we've got carbonate alkalinity. Any kind of carbonate or bicarbonate that enters into the boiler will volatilize, form CO2. And so again, we want to discharge any kind of CO2. So certain traps vent air very well, some don't. Float and thermostatic is obviously a float trap with the additional thermostatic element, and then the thermostat closes when there is no air in the system, and it opens when air is present. So it discharges air very well. As opposed to the inverted bucket has a tiny little air hole on top of the bucket, and that's what it uses for venting out non-condensables. So not terribly good. All the air has to go through that tiny little hole. Thermodynamics, like for example, let's say controlled disk type thermodynamic, it actually won't vent air at all. So what they have to actually do is make sure that that controlled disk has a rough enough surface that it doesn't actually seat 100% tight so that air can leak past the disk. So the correct answer was float and thermostatic. F&T is just shorthand for float and thermostatic. So it has both a mechanical element that operates on the density difference between condensate and steam. And as condensate builds up, the float rises up and discharges condensate. And as for the thermostatic element, there it is. It's sensing the presence of air or non-condensables, opening that and discharging it. So let's see who the big wiener is. Who's the big wiener? Caden. Good job. All right. That was our morning fun. So we're going to get more and more into that stuff as we go along. And we'll take a look a little bit more at some of those characteristics. As for now, back to the grind, back to the piping stuff. Oh, here we go. And there are a couple of little things that I didn't look at yesterday when we were going through it, and just thought I would bring your attention to some code references, because that's the kind of guy I am. Okay, we looked at that big pipe and types of pipe connections, threaded, flanged, and welded. And we really didn't spend much time on threaded. So just so you know, this is an ASME code. This is not the B31.1 piping code, nothing like that. Like I said, ASME makes a bajillion different codes for all kinds of different things. And this is a code that is for people who want to manufacture malleable iron threaded fittings. So malleable iron, if you recall, is a form of cast iron. It's more ductile, it's more malleable than great cast iron. And so this tells us a little bit about malleable iron threaded fittings. First of all, they come in two classes. One of them is a class 150, and the other one is a class 300. So this is something that you're going to find when it comes to flanges as well. Flanges are class 150, class 300, and on and on and on. But the markings are different. So all you get on a class 150 is just the manufacturer's name and trademark. And so some fittings, it might just have, say, a little diamond on it. And you're going to go, well, what the heck is the diamond? The diamond is a unique manufacturer trademark for the XYZ company. And you'll find another one's got a, I don't know, a heart on it. I'm just making this shit up, okay? But so maybe the heart is the YXZ company. So, you know, they would just have some kind of a symbol that represents their company. But if it's a class 300 fitting, it's got a little bit more. Manufacturer's name or trademark, yes. But it will also say the numbers 300 have to be on the fitting. This is a threaded fitting. You pick up a threaded elbow and it says 300 on it, you know it's a class 300 fitting. And the letters MI to designate malleable iron, and size. So if it's a 2-inch or whatever. So what is meant by class 150 and class 300? These classes are service ratings based upon pressure and temperature, because we know that as temperature goes up, the strength of the material goes down. So, you know, some people say, well, that class 300 fitting is good for 250 psi. Well, my answer to that is, at what temperature? Okay, at what is always a matter of temperature. So let's see what happens. Here we've got temperature degrees Celsius, and here we've got a mighty low temperature and a class 150 malleable iron fitting is good for 20.7 bar. That's the And what is a bar? A bar is 100 kPa. Is that what it is? Somebody help me here.
Yeah.
Okay. All right. Thank you for that. So a bar is 100 kPa. So you can say that that's 2.07 megapascals. Okay. To put this into kilopascals, we just times 100. So what we find is even though it's 2070 kPa up to 66 degrees Celsius, you get to 150 degrees Celsius and it's only good for 1280 kPa. Then you get to 175 and it's only good for 1050 kPa. And then there's there that warns you, says, wait a minute, buddy, don't go above 186 on that. Okay. So, but a class 300 fitting, here's the various sizes. So a class 300 fitting, let's say it's a 1-inch NPS fitting, much higher pressure rating. But again, the pressure rating drops as the temperature increases. So if somebody says, oh yeah, I've got a class 300 fitting, it's good for 250 psi, you have to say, well, at what temperature are you talking about? And you have to say, well, what size is the fitting? A smaller fitting has got a higher pressure rating than a larger fitting. So you don't have to memorize this. It's in the PowerPoint if you've downloaded it for your reference. It's just a little bit of good reference material you can put in your back pocket, and if somebody wants to bullshit you, you can call them on it. The next thing is threaded joint limitations. Okay, this one's in 31.1, which is the power piping code, and it basically says, hey, you exceed these limits, you can't use a threaded joint. So let's say we've got an NPS 3 pipe. Well, if we've got a threaded joint, we can't use it for more than 3 megapascals. If we've got 2-inch, we can't use it for more than 4 megapascals. You get the idea. All right. So one of the things we're talking about is different types of pipe connections. So obviously, threaded joints have lower pressure limits than, say, welded joints or flange joints. And we looked at that. And this is actually where we left off. I skipped those slides before, but thought I'd pull them out because it's more interesting than just looking at this stupid shit. So types of flanges: slip-on, welded, neck, blind, threaded, Van Stone, etc. Now, I wanted to zip in on this Van Stone, and that's a term you should have heard in the 4th class. And what we have then is the flange is actually loose. So it spins around on the pipe, which makes things very easy to align, but kind of has limitations in terms of its pressure suitability. Now, just like those fittings, we saw that there's a class 150, there's a class 300, but for flanges it goes even higher. And what we find is that these classes of flanges, the highest number is the highest pressure, just like we saw with the other fittings. So, what do we need to find on flanges? Again, this is another ASME code, and this is a code that's all about flange identification marks, and it's the B16.5 code. You don't have to memorize it, okay? This is just to give you an idea the kind of stuff that you need to find marked on a flange. If you don't find markings on your flange, or if you don't find markings on your fitting, what you do is you take it and you throw it as far as you can toward a dumpster, hoping that you don't hit anything, okay? You don't want to use any unmarked fittings because you have no idea what their quality is and you have no idea how they're going to behave under load. So everything has to be identified. So what we need is a manufacturer's name or trademark, yes. We will need to have a pressure rating class. So class 150, 300, etc. Now, on the flange, it should say B16 or B16.5, one or the other, because what it's referring to is that that flange meets the requirements of that code. The next thing is an NPS designation. So if any of you are doing pumps in the lab, take a look on the flanges. Those are weld neck flanges on the pump lab. And look at the actual flanges, look for these markings. Now, one other thing is if it's a plate or forged, marked with the ASTM specification number and grade identification symbol. Well, you know what ASTM is, and if it's ferrous, it's going to be an A, and then it'll be the material specification, A105, something like that. So look for some kind of marking on the flange that says what the material designation is. See what the class of the flange is, and also look for that, okay? And if you're not in the pump lab, if you're in the boilers lab, if you're on boiler 2 or boiler 4, find a flange and look for this stuff. Now, boy, oh boy, oh boy. Okay, there's a lot of stuff on this one here. Okay, let's start here at this table A361. Where did I get this out of? I don't know. I can't remember where this table is from, but it's from an ASME code. I think it's from B31.1. I think it is B31.1. And so it's got the MOP, okay? And then it's the B16.5 class, which we just looked at, the 150, 300, all the way to 250. Okay, so increasing in class. And then this is for steam service at saturated temperature, so saturated steam, okay? So if it's in saturated steam service, a class 150 flange is only good for, oh, damn it, this is in PSI. Okay, 205 PSI. You can do the math. Times 6.9 gives us KPA. And the class 2500 flange is good for, oh boy, 3200 PSI. Isn't that critical pressure? Oh, look, it says here, note 3 says the rating exceeds the critical pressure. So yeah, I looked at that and I thought that's a honking big number. So if you've got a class 2500 flange and you've got a supercritical boiler, well, that's probably the class of flange that you'd be using on a supercritical boiler. But notice that if we are using in boiler feed water service or in blow-off service, recall that we have this thing that we call shock service. And feed water and blow off is shock. That looks like shork. Every time I write that, it looks like shork. Shock service. And if you recall, B31.1 says, well, we take the MOP of the boiler and we have to add 225 PSI or times 1.25, and that would give you what exactly is the design pressure for the boiler feed water line or for the boiler blow-off line. But now let's take a look at that 150 flange, which was good for 205 PSI. But in shock service, it's only good for 170. Let's take a look at a class 600. These are very, very common. Class 600 flanges. They are good for 1130 psi under saturated steam service, but give it shock service only good for 935 psi. Are you as interested in this as I am? Because I sure am. Now, a standard class reproduce. Okay, standard class. Working pressure by classes. This is Fahrenheit. Yeah, you get the idea. No more of that. Okay, so for flanges, typically we're going to have a raised face. If you don't have a raised face on your flange, you probably shouldn't be using it because it's for a lower type of pressure application. That raised face there makes a relatively small area, and so that when we pull up the bolts, it has a greater compressive force on the gasket itself. Now, the next thing is this unconfined gasket. So if I put a gasket there, that gasket is exposed to the fluid on one side, okay, exposed to the fluid on the inside, and it's exposed to the atmosphere on the other side. So what unconfined means is that the gasket could blow out under certain circumstances. Like maybe you didn't tighten it up enough, maybe you tighten it up in the wrong bolt sequence, maybe the gasket is too thick, maybe you're supposed to use a thinner gasket for that particular pressure. Or maybe you got a gasket that's susceptible to some of the materials that are flowing through the pipe. And so an unconfined gasket, because it's exposed to the fluid, could blow out, and then we got a real mess in the powerhouse. So now this is a straight face flange, and this is just bad news. We just want to stay away from these. These ones would be like, I don't know, if maybe you got a swimming pool, a large industrial pool where the liquid isn't very high pressure and it's circulating through a filtration system, and these are cheap flanges. Again, the gaskets are unconfined, and we're just going to try and avoid these things. We don't see these very often at the plant because they have got this very large surface, and so it's very hard to get an appropriate amount of compressive force on the gasket to seal it up nicely. Now, sometimes people will combine one of these raised faces and they'll bolt it up to a straight face, and you can't. If you want to do it, you have to actually grind off that little piece and make it flat. Now this is a ring joint flange, and so here you can see the gasket. Okay, and the gasket actually fits inside of this joint. So this is a fully confined gasket. This gasket is not exposed to processed materials. It's not exposed to the air. Once this is all bolted up, and the likelihood of a blowout is very, very low. So notice that these come in ANSI 600 or higher. So really, we're talking about a higher pressure service, and also good for higher temperatures. So over 427. It'll be the appropriate material to withstand that kind of temperature. Now there's also a tongue and groove type, which is again a fully confined gasket. So This here is the tongue. And this here is the groove. And so, you know, the gasket fits into the groove, and then the tongue actually compresses the gasket into the groove. It's like a higher pressure type of design. It's costly, and actually this one here is also a costly flange. Okay, so that's it for flanges. Now we're going to go on to backing rings. I thought I had another slide in there somewhere, but nah. Backing rings. So if I'm going to be welding a pipe, so I have plain-ended pipe, and there's my weld. Okay, now when welders certify, okay, if I want to be a certified pressure welder, what I have to do is take my pipe and I have to bevel it along the edge. And I'm going to have a little bit of a gap in between the two pipes. And then I'm going to make a tack weld here. And I'm going to make another tack weld. And the reason for the tack welds is to hold the assembly into place while I complete my weld. Once I finish the tack welds, I call over the weld inspector and I say, hey, examine my tacks. And the inspector is going to look for penetration into of the weld surfaces, but is also going to look for cracks. You cannot have a crack in a tack, because then that crack becomes part of the weld, and that's no good. So after it's tacked up, then what the person does is puts in the root pass and calls the inspector over again and says, hey, check out my root. Inspector looks at the root and makes sure it's a good root. And then the welder then continues to fill and cap the weld. So basically complete the weld. And then it goes through destructive examination and maybe non-destructive examination. Okay, so that's the process to become a certified pressure welder. You cannot use one of these. Okay, illegal. If you do use one during your welding test, then you are limited to only using a backing ring. And no manufacturer, no pressure vessel builder, no piping fabricator hires guys who can only use backing rings. What they want is, can this person actually fill the root without burning through, without making globs of metal inside of the pipe, which we call grapes. We don't want grapes in there. That would be called burn through. It's a bad thing. So the welder has to be talented enough at welding that they can put in a root pass without any burn through and with full penetration. But what if you, well, I mean, if you want to, you can use a backing ring. They're sometimes used. Why and when are they used? Well, obviously the weld specification, the weld procedure has to call for it. So if it's a pipeline welding or something like that, and they say that you have to use a backing ring, you use the backing ring. The engineer might specify it. Where they're used would be to help align the pipe. So let's sort of take a look where that backing ring would be. It would be at the weld joint, inside the pipe. Okay, and here it is. So now when I'm putting in the root pass, I'm not going to burn through. So some are removable, but most of them stay in place. So uh, if it stays in place, there are some potential problems. Erosion, corrosion. So we saw caustic gouging underneath the backing ring in one of those slides, flow restriction, and also the ability to inspect the weld. So generally they're frowned upon, but if a weld joint designer specifies a backing ring, then they put in a backing ring. Oh, by the way, sometimes they're called backup rings. You should probably know both terms. Backup ring. Then butt welding. So most a pipe is going to be butt welded. So sometimes, like for NPS 2 and smaller, we'll use socket welding, but only when we've got a fitting. And for socket welding, what we have is the pipe actually gets inserted into the fitting a certain length. Okay, so here's the edge of the pipe, and they'll leave a little gap in there for expansion and contraction. And then they put a fillet weld all the way around, a full penetration weld to secure the pipe to the fitting. And they'll do the same thing here. They insert the pipe, leaving a little bit of a gap. Okay, and then full penetration weld. So that's not butt welding. Okay, that's it's not butt welding. I just had a brain fart there. But butt welding is when we take the pipe, we bevel the end of it, we leave a little bit of a gap. Okay, the gap is G. So there's a little bit of a gap there. And we might also grind the surface a little bit. If we grind the surface, that's called a land, L-A-N-D. And the land is there to help prevent burn through. So instead of having really thin metal right at the tip and really thin metal there, what we have is sort of a little bit chunkier metal, so it helps to prevent the burn through. And then as for the bevel, this is showing 35 degrees. Often a pressure welder will do 37.5 degrees. And a 37.5 degrees gives you a 75 degree with included angle. And so then this would be done by the weld tester. And if the welder can do this without a backup ring, then they get a pressure welding license for welding pipe. Okay, let's take a 10-minute breather. Hey Google, set a timer for 10 minutes.
10 minutes, and that starts now.
Hello, we're back. One other thing on the slide here, talk about pipe materials, pipe thickness. Depending upon what kind of material and depending on the thickness, we might have to preheat the material. And we might have to do post-weld heat treatment, which is sometimes called stress relieving, but they're not exactly the same thing. But post-weld heat treatment and preheating are both ways that we try to prevent martensite formation. If you recall that martensite formed when we cool off metal extremely quickly, and it forms that brittle body-centered tetragonal that we call martensite. And so that's what we don't want to form. And so what we can do is preheat the metal that's being welded so that it cools off slowly, so the weldment cools off slowly, or what we can do is post-weld heat treat it afterwards. So when we get into welding, we'll take a look at more of those techniques. And again, we have to have qualified weld procedures that have a CRN. I turn that off. There we go. So we have to have a CRN, plus we must have welders that have got the correct performance qualification. So, this is one of the reasons why welding is more expensive, but, big plants, all of the pipe is welded, other than stuff that you need to take apart for occasional servicing. So, gaskets, what do? Basically, they compensate for minor surface flaws and minor misalignment. So we don't want to have drastically misaligned stuff. We don't want to have major surface flaws on the flange faces. No, it's just for minor stuff. And so then what we do is we compress it. When the gasket gets compressed, it moves into all of the little crevices and voids and misalignments that we find in the flange faces and prevents leakage. We already talked about the unconfined and the confined gasket. There's also a semi-confined type of gasket. The gasket is confined on one edge only. So let's take a look at unconfined. Again, this is flat face that we don't want to use, but this one here is a raised face. Notice that the raised face flange faces are now compressing the gasket. Again, it's unconfined because the processed fluid can get to it and the atmosphere can get to it. The confined here, you can see a tongue and groove, and you can also say the ring joint does the same type of thing, where the actual tongue and groove assembly, once this is properly compressed, there is no access to the gasket by the fluid that's inside of the pipe. Now, a semi-confined is, somewhere in between the two. Here you can see the gasket, though it is exposed to processed fluid and the pressure inside the pipe on one side, it's not on the other side. It's protected by this sort of shoulder here. So that's the male-female. And then we also have this type where we have basically a flat face flange combined with a groove. So we talked about ring joints. Why are we back there again? So as for types of gaskets, we can have metallic, metal jacket, spiral wound, various non-metallic ones, so cork and rubber, pretty common. Teflon, also very common. Graphite, compressed asbestos fiber. Yes, we still see asbestos being used in gaskets. So if it's ever your job to remove gaskets in a plant, somebody says, yeah, I need you to, we got this pipe apart, or we got this pump housing apart, I need you to clean up the gaskets. Find out what the gasket material is first before you clean it, because if it contains asbestos, you have to be extremely careful. I can tell you a story, but I won't, and it involves me and it involves asbestos. It involves not knowing, so not good. So here we can see just a solid flat gasket made of metal, serrated. I don't know, this is in your textbook. I don't like these, but corrugated metal gasket, I think is quite important. But actually, this is what I was thinking of. Metal jacket, soft filled gasket. No, actually, I was thinking of this here, spiral wound gasket. These here, very, very important for us. I have seen these used for boiler manhole. And also very important for natural gas. And they likely use these inside the lab for our natural gas piping where we have got a gasketed flange. So what you have is a whole series of spirally wound, actually it's just a single spiral wound sheet that is in that shape. And so they wind that, it's usually like a stainless steel or something, wind it around multiple times, and then they put a filler in there, a filler material in between all of these windings. And so the flange face compresses on it. And there are some solid rings that go all the way around the gasket that are there to prevent you from over tightening. So you can compress it until you get to that thickness, at which point the gasket will compress no more. You don't want to over compress it. But my one word advice to everybody with gaskets is gaskets are single use. It's not like they cost you $800 a piece. Once they are compressed, they lose their resiliency. What I used to do when I was a boiler inspector is I used to go into plants and I'd see the manhole gaskets and handhole gaskets kind of like piled up on the corner, and I could tell that they were used because they're kind of hard and maybe starting to get a little bit brittle, maybe they're cracked just a tiny little bit, but they were definitely compressed. They were used at least once. And so I would go by the gaskets that were piled up, and I would have a utility knife in my pocket, and I would cut them. I'd cut them in half. And every once in a while, one of the engineers in the plant would go, "Well, what are you doing? We were going to reuse them." And I'd say, "Really? You were going to risk your life for a $2 gasket?" So, yeah, do not reuse gaskets. One of the things that is not in here has to do with gasket surfaces. And just a little bit of information. So here's oh, that's a ring gasket. Let's go back to something like here. No, that's no good either. This one here. A lot of these gaskets will have ridges, and maybe they're spiral. Okay, and you think, well, what the heck? This is, a lousy machining job. The whole idea with the ridges is to help hold the gasket in place and prevent blowout. So I just wanted to slide that one in there for you. Ridges prevent blowout. Okay, I digressed. Now let's see where we're going to go. We are going to go to the effects of temperature. Oh, okay, I'm going to open this up to the room. You tell me what the effects of temperature on piping are. I'm all ears. Shout it out anytime you want. I can't even see your name.
The higher the temperature, the weaker the piping.
Okay, there's a good one. Give me another one.
Thermal shock.
Thermal shock. Excellent. Give me another one. Think of things that we've actually covered.
Would water hammer come into play?
Water hammer. Maybe not so much the thermal shock or the high temperature. I think that that's just mostly percussive shock.
Okay.
So
Okay. Should we talk about creep?
creep. Oh, I'm so glad you said that because that's one of the things, weakness at high temperature. Creep.
Okay.
Perfect. Anybody else got something?
There's brittleness at low temperatures.
Son of a gun. We think of the effects of high temperature, but it doesn't say effect of high temperature in the objective. What about the effect of low temperature? Low temperature brittleness. Yes. Depends upon the type of material. And so for a low temperature, a cryogenic steel piping system, we would want to assure that it's got some kind of an alloy in there like nickel to improve its nil ductility transformation temperature. Okay, I think that that's enough. I'm going to go to the next slide and see what I got down there. Creep, thermal shock, brittle failure. So we think too of thermal expansion. That was right on the slide. And where we've got thermal expansion, we may in fact have restricted thermal expansion, which will cause increased stress on the piping. And those stress concentrations can lead to failure. And then this one here, graphitization, is one of the things we said occurs over 425 degrees Celsius, where the carbide phase reverts to graphite and weakens the pipe. So that is also related to the weakness that Osagbavo had said, weakness at high temperature. So you did a great job on that. I want to talk a little bit about thermal shock. And so let's say that I have got a pipe that is at extremely high temperature, and then I splash cold water on it. So I gotta have a cold color here, blue. Okay, I'm splashing cold blue water on it. Well, what happens is I get immediate thermal contraction at the outside skin, if you will, outside surface. But I don't experience that same contraction on the inside of the pipe. Well, what do we get? We can get this pipe can actually shatter, or it can just develop cracks over a period of time due to thermal shock. And the opposite is true. I mean, maybe we get some really cold fluid unexpectedly going through a very hot pipe. Anyway, so thermal shock is really a very sudden onset of restricted thermal expansion. Restricted thermal expansion or contraction. I should have been a doctor. With handwriting like that. Now, gonna skip that one. Okay. Now, of course, when we have got expansion, we need expansion joints. To study this, go over it, but sort of the broad categories are the bellows type and the slip type. And the slip type, we've got a pipe inside of a pipe, and we've got a lubricant and a sealant and a packing gland and all this kind of stuff. This particular one has a built-in anchor. I thought I'd point that out. And where, the bellows is basically an accordion. Now, as for the slip expansion joint, they, in particular, well, I mean, all of them are sensitive to correct alignment. You have to have the pipe going in, not on an angle. It's going to be going straight in. And so to make sure that these pipes go straight in the way they're supposed to, we are going to need guides and we're going to need anchors. Now, unlike the bellows type, really doesn't require any maintenance other than occasional inspection. This one here, as part of the inspection, we'd also be greasing it and perhaps taking it out of service and replacing packing. I'm going to skip that. Now, there's this thing here that is correctly called a tied universal expansion joint and is covered in your third class. And this one is neat because we don't have to worry so much about anchors and guides. These particular expansion joints, they are bellows types, and they actually accept a considerable amount of axial misalignment. So let's take a look at that term, axial misalignment. So let's say I got two pipes here, and I can mark the center line being the axis, and if they are axially aligned, they share the same center line. But if they are axially misaligned, then they obviously do not share the same center line. So they will accept axial misalignment. They will also accept angular misalignment. So angular misalignment is I got a pipe like this, I got a pipe like that, and they are angularly misaligned. Not only do they accept it, but they're designed for that. So we have these things here. These are called gimbal mechanisms. They don't all have gimbal joints, but this particular one in the picture has gimbal joints, G-I-M-B-A-L joints. And that's really what permits that axial and angular misalignment. So where do we find something like this? Well, think about this process vessel here, a fairly tall vessel, and I had a really good explanation of that, but I'm going to skip my explanation because I can't remember what it is. And then we got these pressure equalized expansion joints. I'm not going to get into that because I'm just so excited about some of the stuff that's upcoming. So as for axial movement, so let's say here I've got an anchor. And so here's a bellows expansion joint. There's another one. And what I have are guides. And the guides are very important so that I end up with axial alignment. And so now, when there is change in temperature, there is axial movement, but there's no misalignment. No misalignment because we anchor it and we have guides. Now, so here you can see we've got axial misalignment. And here you can see we've got angular misalignment. And so, one of the reasons that we have the guide and the anchor, everything can be installed correctly to prevent this type of stuff. Okay, we don't want this happening. This here is what we want. This is what we don't want. Unless we use a special type of expansion joint called a tied universal expansion joint. And if it's tied universal, it's A-OK. It's designed for this. So, movie number 1. Come on, start. Start. Why doesn't want to play?
You have like the
Maybe
pen active?
Yeah, I just realized that. Thank you. Well, then I'll just use. Why can't I activate? No, there it goes. Erase all the ink, and then how do I deactivate the pen? Maybe I just need a pointer. Nope, I don't want that. Well, we'll go back there. Now it's showing me pen again. Why can't I turn off the pen? What turns off the pen? Does that turn off the pen? Nope. And I didn't want the subtitles. I mean, white? It's still a pen. That's a slide sorter. This is something else. That's audio, apparently. No, that's not what I wanted it to do. Okay. What have I done? Okay, we'll just get this going all over again here.
They really don't make it
I
easy
can.
for you, huh?
I'm doing this on purpose, just to entertain you. It's gonna work.
Scott, you can make it easier on by learning the material beforehand.
Oh, okay, right on. Okay.
Okay, enough burns. All right, that's video number 1. Here's video number 2. Well, so there you go. Expansion joints, expansion bellows, anchors, and guides in 5 minutes. This guy did more in 5 minutes than I can do in 3 hours. The links are up to these, and they're obviously they're in the PowerPoint. So what I'm going to do is make sure that you get that posted up on the the slightly modified PowerPoint from the one that was used in the past. I'll make sure that that's up so you guys can follow the link, watch those videos at your leisure. So then piping supports, and you'll see maybe some of the stuff in the Synovus lab, but basically we're trying to support the weight of the piping, and we can either have rigid supports or we can have spring supports. So we can support the pipe from the bottom, we can have an overhead hanger as well. So let's see if I'm going to work this time. Oh, I'm not going to work this time, am I? All right. So let me see, how can I get the pen back? There we go, there's a pen. So this here is a spring type of support. Big spring in there, and the pipe would rest on top of it. And this would be mounted, anchored to the ground. Now this one here is very, very commonly used, where you've got sort of a vertical run of pipe, and at the base of the elbow, they'll have a support welded right into the elbow. And in case there's damage to the pipe on the inside and it starts to leak, what happens if that leak or that crack occurs right where the support is? Well, what we're going to do is have a little hole in here somewhere, and the hole is called the telltale, and that way we're going to know if this thing has started to leak. And it's called a constant support hanger, and what it has is a spring and a lever mechanism, and the whole idea is that it always is designed to support a constant load. The main thing is we're trying to prevent the pipe from sagging, and also to allow a certain amount of free movement as it expands and contracts. So B31.1 power piping code says something about pipe supports. Do we have to support it at regular intervals? Now maybe we've got a common bracket, and maybe there's a small pipe and a large pipe. Well, what we'll do is we will support both pipes at intervals that are appropriate for the smallest pipe, because a small diameter pipe isn't very rigid. It's kind of like a limp noodle, and so we have to support it more frequently. Whereas a big, hefty, a 6-inch pipe is pretty massive, and it's probably not going to need to be supported at such close intervals. Now, there are roller supports, and we'll take a look at those in a bit, but roller supports are very common, and especially where you have a long length of steam line and where we're going to expect a lot of thermal expansion and contraction. And also it says we don't support branch lines from vertical pipes. So if I got a vertical pipe like this, okay, and there's a T, we can't use this vertical pipe here as a support for the T, for this branch, because there'll be excessive stress right here, and it's gonna crack. So there's a table in B31.1. You don't have to memorize this. All you need to know is that this information is available for you as a power engineer, and there's a place where you can look to find out regular support intervals. So let's say we've got steam and we've got NPS 2 pipe. We should be supporting that pipe roughly every 4 meters maximum. If we've got, say, a 6-inch NPS pipe, that interval increases to 6.4 meters. And if we got an NPS 1 pipe, And probably you can say the same for NPS 3/4 or 1/2 inch pipe or whatever, about every 2.7 meters. Okay, so that's from the 31.1 piping code. There's an anchor. There's a spider guide like they showed you in the video. I thought the video was great. I just really enjoyed that.
Dave,
Yes.
is there any code that kind of recommends kind of support for different purposes? Like I saw we have different kind of supports, okay? So is there any code that will like, okay, for this kind of purpose, this kind of support you're going to use? I mean, how do you really pick support? How do you choose the different kind of support for applications?
Well, the first thing that I would do, and frankly, I've never had to do that, but if I was to do that, I would first of all take a look at the relevant piping code. So if it's a refrigeration piping code, I'd pull up the B31.5. If it was a process piping application, I'd pull up the 31.3. If it was steam, I'd pull up 31.1. And I would look over that and I would see exactly if there are specific requirements for constant support hangers or spring type of supports or rigid supports. Okay. That's where I would start. Unfortunately, I can't answer your answer directly, but I can sort of tell you, where to look. Okay. That's it for piping. That was a good question. So I did promise we were going to get into traps, and we got 15 minutes left in class, so I guess we'll go ahead with that. Okay, so this is the next chapter. This is chapter 5. And I think you know a lot of this stuff. It's about separators and the purpose of traps. And so, we want to get condensate out of the steam lines. We want to prevent water hammer. We want to promote heat transfer by making sure that all of the condensate drains from heat exchangers instead of our heat exchanger being half full of condensate. We want to maximize the heat transfer surface area. We want to recover condensate, so put it into a condensate return system because ultimately it's pure water. And maybe, just maybe, we don't want water for turbines. Disastrous. So what else do we do with steam traps? We vent air in non-condensables, as I already mentioned. And then, very important, we prevent steam from entering the condensate system because the steam has all of that latent heat, all of that energy that we want to apply to its intended purpose. We want that steam to be going through turbine blades, not out through turbine casing drains. Okay, we want the steam going through blades. We want the steam to be residing in the heat exchanger and liberating its heat to whatever process fluid is that we're trying to heat up. We don't want it blasting through into the condensate lines. So that's why they call it a trap. They trap the steam to where it's supposed to be, but at the same time, they let out the condensate. So this, I think, is a really good PowerPoint page if you just wanted a synopsis of everything that steam traps do. And where do we put them? Well, let's say I got a steam main here and the steam is flowing this way, and in this case is going into a heat exchanger over here. Well, assuming that this is saturated steam will be condensing. Even though it's well insulated, um, the steam line is insulated, we still will get some condensation. So we have to get rid of the condensation. We might have a steam separator, and you have seen those in the Synovus building in the main floor lab. What do we find at the base of the steam separator? A steam trap discharging a condensate back into the condensate return system. So maybe we've got, 90% dry and saturated going in, and maybe what leaves the steam separator might be, say, 98% dry and saturated. Now, where we get a reducer in the pipe, say we've got 4-inch pipe NPS 4, and maybe we've got a 2-inch pipe here, so we've got a 4 to 2-inch reducer. We'll make sure we put a steam trap before that point. If we have an expansion joint, not so much a bellows type, but I couldn't find a nice small picture of a slip expansion joint, but at expansion joints, there are usually little pockets where condensate can collect. So another place to locate a steam trap. Now, when the steam enters a riser, as opposed to a main, at the base of the riser, we will have what's called a drip leg. And sometimes people call it a drip pocket. But at the base of the drip leg, at the base of a riser, we're going to have a steam trap. Now here we got a control valve, and the control valve is going to throttle the amount of steam in order to maintain the process conditions at the heat exchanger. So sometimes it's going to be open. Sometimes it's going to be, part way open, 50-50. So it modulates, and maybe it's going to be shut, or maybe that valve is on off, in which case it's either open or shut. During the times when it's shut or close to being shut and the steam flow is very gradual through that control valve, we'll get a lot of condensate formation upstream of the valve. Then what happens when it opens? Let's say it's a solenoid valve, open. Oh man, we get this slug of water going through that steam line, all kinds of water and damage to the downstream equipment. So upstream of control valves is a very, very important place to locate a steam trap. Sometimes we take the heat exchanger or the piece of equipment out of service, and we have a little isolation valve there. So let's say we close that isolation valve, or doing some tube repairs or something like that, or maybe this heat exchanger just simply isn't going to be in service for a little while because we've alternated. We go back and forth from heat exchanger 1 to heat exchanger 2. During the period of time when that isolation valve is closed, again, we're going to accumulate a lot of condensate above that valve, and we have to get rid of it. So we locate a steam trap on the upstream side of isolation valves. And then finally, let's say we got heat exchanger, maybe we got a steam turbine, because we know that our steam turbines have casing drains to get rid of the condensate during warm-up period until that turbine is heat soaked. So again, we want to have a steam trap, and that's where we put them. So when you are in the lab on the first floor of the Synovus, take a look at where the steam traps are located. I know in year 1, you trace lines and it's all very, very new to you, and you run turbine 1 and boiler 1 and turbine 3 and boiler 2 and all that kind of stuff. But this time around, take a close look at exactly, oh, there's a steam separator. Is there a trap on that steam separator? What kind of trap is it? Look for the expansion joints and see if there's a trap, and ask yourself why or why not. If you see the base of a steam riser, is there a trap? What kind of trap is there? And on and on and on. So operation. So we talked about the three types. So here's sort of a little bit of a different way of looking at the operation of a thermostat. It's sensitive to temperature difference between steam and condensate. Okay, and here's another way that we can comment on it. It requires some amount of condensate to subcool in order to open the trap. So if I've got a thermostatic trap here, and that's just a very simple symbol for a trap. When the steam goes in, if it's at saturation temperature, let's say it's 200 Celsius, it's going to have to subcool to, I don't know, it's a high pressure trap, by the way, maybe 180 degrees Celsius before that trap will actually open and discharge the condensate. Okay, so think about that. Think of the subcooling that must occur with a thermostatic trap in order for it to actually operate. And then compare it to a mechanical trap. A mechanical trap doesn't care one bit about subcooling. Doesn't care. All it is sensitive to the density difference between steam and condensate. So in this case, what I have is usually some kind of a float mechanism, and I got condensate that is flowed on top of, and as condensate builds up, it discharges. And if condensate is building up very rapidly on a constant basis, then it will continuously discharge condensate. It doesn't care about subcooling. And as for thermodynamic, well, what is that sensitive to? I mean, we talk about sensitivity, right? This is sensitive to temperature. The mechanical is sensitive to density. And the thermodynamic is sensitive to the differences in energy between steam and condensate. And so this is where we get these thermodynamic traps like the control disk and what have you. So just a little bit of a different way of looking at these operating principles. Thermostatic, oh boy. Let's stop here. We're done for today. Any questions before we officially totally shut her down?
I have a question, Dave, just about code, not really with this, if you could help. With
Sure,
the
Andrew, yep.
extracts, I know you gave us, I printed off the two that you sent to us, the 31.1 and the ASME BP VC2. But you know those extracts that Pan Global sells? Do they have everything that this has, or do they have more? What's really in those?
They have a lot more, And so if you want, what we could do is go on to that Pan Global. And frankly, I think that they're fantastic. Let's just go back here and see, is this going to work? There we go. Okay. And so let's go to Pan Global. Global Training Systems. And okay, we'll just go there, and then somewhere they've got the bookstore, textbooks, and Canadian products. And let's just see exactly what's in there. Codes and extract supplements. Actually, it's these two here. There's this one here, which is ASME 1, ASME 4. Well, let's look at it. So this is volume 1. So it's got ASME 1 power boilers, but not the whole thing, but just the academic extract. It's got ASME 4, which is heating boilers, 8 Div 1, which is pressure vessels, and 31.1 powered piping. Okay, it says it's essential for students from 4th class to 1st class, as well as students in the 2-year technology programs. Now, I'm not blowing smoke or bragging or anything like that, but I'm the person that compiled this code book, because I don't know if you guys knew, but I worked for Pan Global for about 3 years. I was one of the things that I was the chief technical editor toward the end of my tenure there. And so one of the things we had to do was update from the 2004 code. And so I worked very closely with the director of SOPEAK, a guy named Tom Lemming, to find out exactly what students need for the examinations. So this is the second volume. This is volume 2, and this one here is ASME Code Section 9, which is welding. It's got 31.3 process piping, and it's got ASME 2D materials. So I think that this is really good for a 3rd class, I think, but definitely when you get into 2nd, you should have this and you should have that one. Okay, the reason is because once you get code questions at your 2nd class or 1st class level, you absolutely need it. Or full code.
Awesome. Thank you very much.
Okay, and maybe you can get those used too. I don't know. You might be able to save yourself some money. Now, then the other thing is, of course, you can do this. Share application screen. Let me put this back on. Allow. And I was telling people, now you might have to take your computer to school with you when you go to lab, okay? Go to the Reg Earhart Library online. And then you'll see that there's an A to Z list of e-resources. And when you go through that A to Z list of e-resources, A is for ASME. So go to the ASME Standards collection. And it'll take you to a place called TechStreet. You might be able to do this from home, or you might have to do it at the campus. I'm not too sure, but it has all of the ASME codes, like whatever you want, it's there. And so what you do is a little search. You go, let's say I want BPVC. Oh, why didn't that work? Oh, that was a sort function. That's not search. Here's search B boiler pressure vessel code. And it gives me a whole list of all of the boiler and pressure vessel codes. And so 12. I didn't want 12, but whatever. So let's say I want boiler pressure vessel code 12. I click there and I can download it. And then to activate it, I need to have this thing installed, which is called the File Open plugin. How did I get there? I clicked over here on the little green trigger, I guess. Okay? So you should be able to download the free codes, the full codes for free. And if you've got the File Open plugin, then you should be able to access those and read them. Okay, time to say goodbye.